Look at this image. This is Jade's GS Z14-0, a galaxy photographed by the James Webb Space Telescope in 2024. According to our best measurements, this galaxy is 13.9 billion years old. There's just one problem with that. The universe itself is only 13.8 billion years old. This galaxy, according to our instruments, is older than the universe that created it. And it's not alone. James Webb has found dozens of these impossible galaxies, each one contradicting the fundamental timeline of cosmic existence. What you're about to learn will change how you see the universe forever. I've been obsessed with this mystery, because this isn't just about one anomalous reading or a single miscalculation. This is about a pattern of discoveries that suggests something is fundamentally wrong with our understanding of cosmic history. And the more we look, the more impossible galaxies we find. Before we go any further, I need you to understand something crucial. The existence of these galaxies doesn't just challenge one theory or one measurement. It challenges the entire foundation of modern cosmology. The Big Bang Theory, the expansion of space, the formation timeline of the first stars and galaxies. Everything we thought we knew about how the universe came to be is now in question. And the scientific community? They're struggling to explain it. Some are proposing radical new theories. Others are questioning our most basic assumptions about time and space. And a few are wondering if we've misunderstood the universe's age entirely. So how did we get here? How did a telescope designed to peer into the early universe end up breaking our model of cosmic history? And what does it mean if these galaxies are real? That's what we're going to explore today. This is going to be a deep journey, one that takes us from the birth of the cosmos to the bleeding edge of theoretical physics. We're going to examine the evidence, confront the paradox, and explore what it might mean for everything we thought we understood about existence itself. Let's begin. In July 2022, the James Webb Space Telescope released its first images to the public. The world watched in awe as we saw the deepest, clearest views of the early universe ever captured. Galaxies that formed just a few 100 million years after the Big Bang came into focus with unprecedented clarity. It was a triumph of human engineering and scientific ambition. But within weeks, something strange started happening. Astronomers analyzing the data began noticing galaxies that didn't fit the models. They were too bright, too massive, too well-formed, and according to their redshift measurements, they were too old. At first, scientists assumed it was a calibration issue. New telescope, new instruments, there's always a learning curve. But as more data came in, the problem didn't go away. It got worse. By early 2023, papers started appearing in scientific journals with titles that betrayed a growing sense of unease. A population of red candidate massive galaxies at Z greater than 5 in CERS. Spectroscopic confirmation of 4 metal-poor galaxies at redshift 10.3 to 13.2. The language was technical, but the implication was clear. We were seeing things that shouldn't exist. Dr. Ivo Lab, an astronomer at Swinburne University of Technology, put it bluntly in a 2023 interview. If these galaxies are real, and if our measurements are correct, then we have a serious problem. These objects appear to have formed in a time when the universe simply wasn't old enough for them to exist. Let me put this in perspective for you. Imagine you're an archaeologist, and you discover a smartphone buried beneath a layer of rock that's 200 million years old. That's the level of impossibility we're dealing with here. These galaxies are showing up in an epoch when the universe was supposedly still in its infancy, barely past its first few 100 million years of existence. And it's not just one or two galaxies. By mid-2024, James Webb had identified over 30 galaxies that challenge our cosmic timeline. Some appear to be less than 300 million years after the Big Bang, yet they're as massive and structured as galaxies we see billions of years later. They have spiral arms. They have central bulges. They show signs of multiple generations of stars. All things that should take billions of years to develop. Now, before I tell you what scientists think is happening, you need to understand how we actually measure the age of distant galaxies. Because that's at the heart of this mystery. To understand why these galaxies are impossible, we need to go back to the beginning. Not the beginning of this mystery, but the beginning of everything. The Big Bang. For nearly a century, the Big Bang theory has been the cornerstone of cosmology. The idea is elegant and well supported by evidence. About 13.8 billion years ago, the universe began as an infinitely hot, infinitely dense point. Then it exploded outward, expanding and cooling as it grew. This isn't speculation. We have remarkable evidence for this. In 1929, Edwin Hubble discovered that distant galaxies are moving away from us, and the farther away they are, the faster they're receding. This suggested the universe itself is expanding. In 1965, Arno Penzias and Robert Wilson accidentally discovered the cosmic microwave background radiation, a faint glow of light that fills the entire universe. This is the afterglow of the Big Bang, cooled over billions of years to just 2.7 degrees above absolute zero. It's one of the most important discoveries in the history of science, and it confirmed the Big Bang model. The cosmic microwave background tells us something crucial. It shows us what the universe looked like about 380,000 years after the Big Bang, when it had cooled enough for atoms to form and light to travel freely. Before that moment, the universe was opaque, a hot plasma where photons couldn't travel more than a tiny distance before colliding with particles. This map of the cosmic microwave background, created by satellites like COBE, WMAP, and Planck, is one of the most precise measurements in all of science. And from it, we can calculate the age of the universe with extraordinary accuracy. 13.797 billion years, give or take 21 million years. This measurement has been confirmed through multiple independent methods. The expansion rate of the universe, the abundance of light elements like hydrogen and helium, the observed distribution of galaxies, they all point to the same number, 13.8 billion years. So we know when the universe began. Now let's talk about what happened next. After the Big Bang, the universe went through several distinct phases. First came the cosmic dark ages, a period lasting about 100 million years when the universe was filled with neutral hydrogen gas but had no stars. No light, just darkness. Then, somewhere between 100 and 200 million years after the Big Bang, the first stars ignited. These weren't stars like our sun. They were massive, hundreds of times the mass of the sun, burning incredibly hot and bright. We call them population 3 stars, and we've never seen one directly because they all died billions of years ago. These first stars were crucial. They fused hydrogen into heavier elements like carbon, oxygen, and iron. When they died in supernova explosions, they scattered these elements into space, seeding the universe with the raw materials for planets and, eventually, life. Over the next few hundred million years, these stars began to cluster together under the pull of gravity, forming the first galaxies. And this is where the timeline becomes important. According to our models, galaxy formation is a slow process. First, you need dark matter to clump together, creating gravitational wells. Then gas falls into these wells and begins to condense. Stars form from this gas, and over millions and billions of years, they organize into the structures we recognize as galaxies. Small galaxies form first, then they merge over time to create larger ones. This hierarchical assembly is a cornerstone of the lambda-CDM model, our standard model of cosmology. It's been tested and validated through countless observations and simulations. By 500 million years after the Big Bang, we expect to see small, irregular galaxies with relatively few stars. By 1 billion years, we might see some more structured galaxies forming. But massive, well-organized spiral and elliptical galaxies? Those should take several billion years to develop. That's the timeline. That's what decades of observations and theoretical work have told us to expect. Now, enter the James Webb Space Telescope. James Webb wasn't just built to take pretty pictures, though it certainly does that. It was specifically designed to see the first galaxies, to peer back to the cosmic dawn and watch the universe's first light. Unlike the Hubble Space Telescope, which observes primarily in visible light, James Webb observes in infrared. This is crucial because of something called redshift. As the universe expands, light traveling through it gets stretched. The farther light travels, the more it's stretched, shifting from visible wavelengths toward the infrared. Light from the earliest galaxies has been traveling for over 13 billion years, and in that time, it's been redshifted so much that it's now in the infrared spectrum, invisible to telescopes like Hubble. But James Webb can see it. With its massive 6.5-meter mirror and advanced infrared instruments, it can detect light from galaxies that formed just a few hundred million years after the Big Bang. And that's exactly what it's been doing. Since it began operations in 2022, James Webb has been conducting deep field surveys, staring at tiny patches of seemingly empty sky for hours or even days, collecting every photon of light from the most distant objects in the universe. What it found was not what anyone expected. Let me walk you through the process of how we actually measure a galaxy's age and distance. because this is where the paradox becomes undeniable. When astronomers observe a distant galaxy, they measure its redshift. This is represented by the letter Z in scientific papers. The higher the Z value, the farther away the galaxy is, and the earlier in cosmic history we're seeing it. A galaxy with a redshift of Z equals 1 is about 7.7 billion light-years away. We're seeing it as it was 7.7 billion years ago. A galaxy at Z equals 6 is about 12.7 billion light-years away, seen as it was just 900 million years after the Big Bang. Now, here's where it gets interesting. James Webb has found galaxies at redshifts of Z equals 10, Z equals 12, even Z equals 14 and higher. These are galaxies we're seeing as they were just 300 to 500 million years after the Big Bang. And they're huge. They're bright. They're structured. Jade's GS Z14-0, the galaxy I mentioned at the beginning, has a redshift of 14.3. That places it about 290 million years after the Big Bang. At that point in cosmic history, the universe was only 2% of its current age. Think about that. 2%. If the universe were a 50-year-old person, we'd be looking at a photograph from when they were 1 year old. Now Jade's GS Z14-0 isn't just present at this early time. It's massive. It contains hundreds of millions of solar masses worth of stars. It shows evidence of ongoing star formation at a rate much higher than we see in modern galaxies. And spectroscopic analysis reveals the presence of heavy elements, which means multiple generations of stars have already lived and died. But wait, to create multiple generations of stars, you need time. A massive star might live for only a few million years before going supernova, but smaller stars live longer. To build up the kind of heavy element abundance we're seeing in these galaxies, you'd need tens or even hundreds of millions of years of stellar evolution. So if Jade's GS Z14-0 is 290 million years old counting from the Big Bang, and it required hundreds of millions of years of stellar evolution to reach its observed state, when did it start forming? The math doesn't work. The timeline is impossible. And Jade's GS Z14-0 isn't even the most extreme example. In 2023, astronomers confirmed a galaxy designated as CERS 93316 with a redshift of 16.7. If this measurement is correct, we're seeing this galaxy just 250 million years after the Big Bang. And it's bright and massive. Then there's Maisie's galaxy, also known as CERS 2782, discovered in June 2022. Initial measurements suggested a redshift of 11.8, placing it about 400 million years after the Big Bang. When researchers looked closer, they found it had already assembled stars equivalent to several hundred million suns. Glass Z13, another early discovery, appeared to be about 330 million years post-Big Bang. Spectroscopic follow-up confirmed it was forming stars at a prodigious rate. Are you starting to see the pattern? Every one of these galaxies appears too early, too massive, and too evolved for the standard cosmic timeline. It's not one anomaly. It's a systematic problem. Dr. Dan Koh, an astronomer at the Space Telescope Science Institute, described the situation in a 2023 paper. We're seeing galaxies at redshifts where we expected to see perhaps a few small, faint proto-galaxies. Instead, we're seeing dozens of bright, massive galaxies. Either our understanding of galaxy formation is incomplete, or something fundamental about our cosmological model needs to be revised. Most people don't know this, but there's actually a metric called the Schechter function that predicts how many galaxies of different masses should exist at different points in cosmic history. James Webb's observations violate this function at high redshifts. We're seeing 10 to 100 times more massive galaxies than predicted in the first 500 million years after the Big Bang. Remember this detail, it becomes important later. The number of massive early galaxies isn't just slightly off from predictions. It's off by orders of magnitude. Now, before we go further, I want to address the obvious question you're probably asking. Could the measurements be wrong? Could these galaxies actually be closer and less extreme than they appear? It's a fair question, and it's one astronomers have been investigating rigorously. Let me tell you what they've found. When James Webb first started finding these high redshift galaxies, there was immediate skepticism. Photometric redshifts, which are estimates based on the galaxy's color in different wavelength bands, can sometimes be wrong. A very dusty nearby galaxy can sometimes masquerade as a distant one. So astronomers did what they always do when they find something surprising. They went back and checked. They used spectroscopy, which is a much more precise method. Instead of just looking at the overall color, spectroscopy breaks down the light into its component wavelengths, revealing detailed fingerprints of atoms and molecules. And you know what they found? The high redshifts were confirmed. Again and again. Jade's GS Z14-0, confirmed with spectroscopy. Glass Z13, confirmed. Many of the other candidates? Confirmed. There are still some galaxies where the measurements are uncertain, and some photometric candidates have been ruled out. But there's now a solid sample of spectroscopically confirmed galaxies at redshifts above 10, and the number is growing with every new dataset. The galaxies are real. The measurements are correct. The paradox is undeniable. So what's going on? How can galaxies be older than the universe that created them? Scientists have proposed several explanations, and this is where things get really interesting. Because each explanation, in its own way, challenges something fundamental about our understanding of reality. Let's start with the most conservative explanation. Maybe the universe is older than we think. Our measurement of the universe's age comes primarily from the cosmic microwave background and the observed expansion rate, known as the Hubble constant. But here's the thing. There's actually a tension in cosmology right now, something called the Hubble tension. When we measure the expansion rate of the universe using nearby supernovae and other local methods, we get one number. When we calculate it from the cosmic microwave background, we get a slightly different number. The difference is small, only about 9%, but it's statistically significant, and it's been confirmed by multiple independent studies. Some cosmologists think this tension might indicate that the universe is actually slightly older than 13.8 billion years. If the actual age is, say, 14.5 or 15 billion years, that would give additional time for these early galaxies to form. But there's a problem. Even an extra billion years doesn't solve the problem. These galaxies would still be forming impossibly fast. And extending the age of the universe creates other issues. It would require revising the cosmic microwave background data, which is some of the most precise data we have. Dr. Adam Rees, a Nobel laureate who's been at the forefront of measuring the Hubble constant, addressed this in a 2024 interview. Even if the universe is somewhat older than our standard estimate, it doesn't resolve the tension with what James Webb is seeing. These galaxies are forming stars at rates and timescales that don't fit any reasonable extension of the standard model. So if it's not just a matter of age, what else could it be? The second explanation is that galaxy formation in the early universe was fundamentally different from what we see today and from what our models predict. In the standard picture, galaxy formation is a gradual process. Small galaxies form first through relatively slow accretion of gas. Over time, they merge to create larger galaxies. It's a bottom-up approach, driven by the gravitational influence of dark matter. But what if, in the very early universe, conditions allowed for much more rapid galaxy formation? What if gas could collapse and form stars much more efficiently than we thought possible? Some models propose that the early universe had pockets of much higher density than average, seeded perhaps by quantum fluctuations during cosmic inflation. In these regions, gas could have collapsed rapidly, forming massive star clusters that quickly evolved into galaxies. There's also a theory involving supermassive stars. If the very first stars were not just massive, but supermassive, hundreds or even thousands of times the mass of the Sun, they could have produced enormous amounts of light and heavy elements in a very short time. Their deaths could have triggered rapid secondary star formation, jump-starting galaxy assembly. Dr. Pradika Dayal at the University of Groningen has been exploring these ideas. In a 2023 paper, she and her colleagues proposed that top-heavy stellar populations, where most stars are much more massive than in modern galaxies, could explain the brightness of early galaxies. Massive stars are incredibly luminous, so a relatively small number of them could make a galaxy appear very bright. This is an interesting solution, and it's being actively researched. But it has limitations. Even with more efficient star formation, you still need time for the process to unfold. And the spectroscopic data showing heavy elements suggests multiple generations of stars, which brings us back to the time problem. Here's where it gets disturbing. Some physicists are starting to wonder if the issue isn't with galaxy formation at all, but with our understanding of time itself in the early universe. General relativity tells us that time is not absolute. It's relative, affected by gravity and motion. In the intense gravitational fields near black holes, time slows down dramatically. Could something similar have happened in the early universe? The early universe was incredibly dense. All the matter and energy now spread across billions of light years was compressed into a much smaller volume. Some theoretical physicists propose that in such conditions, time could have progressed differently in different regions. Imagine pockets of space where, due to quantum fluctuations or variations in density, time effectively ran faster. In these regions, billions of years of evolution could occur, while only hundreds of millions of years passed in the wider universe. It sounds like science fiction, but the math is based on real physics. Einstein's equations allow for time dilation effects in varying gravitational fields. And quantum mechanics introduces even stranger possibilities, like quantum fluctuations in the fabric of space-time itself. Dr. Nayash Afshorty at the Perimeter Institute for Theoretical Physics has explored related ideas. In papers on cosmological time dilation and quantum gravity effects in the early universe, he suggested that our assumptions about uniform time progression in the early cosmos might be too simplistic. If time wasn't uniform, then what we interpret as impossibly old galaxies might actually be galaxies that experienced a different rate of temporal progression. They're not older than the universe, they just experienced more time than their surroundings. Of course, this is highly speculative. We don't have a complete theory of quantum gravity, which would be necessary to fully describe such effects. But the fact that serious physicists are considering it tells you how profound this mystery is. Now, let's talk about the truly radical explanation, one that some scientists are beginning to whisper about, though most are hesitant to say it out loud. What if the Big Bang wasn't the beginning? For decades, we've treated the Big Bang as time zero, the moment when the universe came into existence. But what if that's wrong? What if the Big Bang was just a transition, a phase change in a universe that already existed? There are several cosmological models that propose this. One is the cyclic universe model, where the universe goes through infinite cycles of expansion and contraction. In this model, the Big Bang we observe is actually the bounce from a previous contraction phase. Another is the conformal cyclic cosmology proposed by Roger Penrose, the Nobel Prize-winning physicist. Penrose suggests that the universe goes through infinite eons, each beginning with a Big Bang-like event and ending in the far future when all matter has decayed. But through a mathematical transformation, the end of one eon becomes the beginning of the next. In these models, structures from a previous cosmic era could potentially seed the formation of galaxies in the current era. Information or structure could carry over through the Big Bang event, giving galaxy formation a head start. Now, I want to be clear. These are fringe ideas in cosmology. Mainstream science does not currently accept them. But the James Webb discoveries are pushing some scientists to reconsider. Dr. Laura Mersini-Houghton at the University of North Carolina has worked on multiverse cosmology and pre-Big Bang scenarios. In a 2024 discussion, she noted, "The Webb data is forcing us to think outside the standard paradigm. If we can't explain these observations within the standard Big Bang framework, we have to be open to more exotic possibilities." And there's one more explanation, perhaps the most unsettling of all. What if our entire cosmological model is fundamentally flawed? The lambda-CDM model, our standard model of cosmology, includes several components we don't fully understand. Dark matter, which we've never directly detected but infer from gravitational effects. Dark energy, a mysterious force causing the universe's expansion to accelerate, which we know even less about. These components make up 95% of the universe's total energy content. We only directly understand the 5% that's normal matter. Some physicists are starting to ask, what if we've gotten dark matter or dark energy wrong? What if there are additional components or forces we haven't accounted for? What if the expansion history of the universe is different from what we've calculated? There's a theory called modified gravity that proposes our understanding of gravity itself might need revision on cosmic scales. Instead of dark matter, the theory suggests gravity behaves differently than predicted by general relativity when dealing with galaxies and larger structures. If something like modified gravity is correct, it could change our entire timeline of cosmic evolution. The age of the universe, the formation of structures, the interpretation of redshift, all of it could need revision. Dr. Stacy McGaugh at Case Western Reserve University has been a prominent advocate for modified gravity theories. In his research on galaxy dynamics, he's found patterns that are difficult to explain with dark matter, but fit naturally with modified gravity. Could James Webb's impossible galaxies be another piece of evidence pointing toward a fundamental revision of physics? It's too early to say, but the possibility exists. You might be thinking, surely scientists can figure out which of these explanations is correct. But here's the reality. We don't have enough data yet, and each explanation makes different predictions that require additional observations to test. For example, if galaxy formation was simply more efficient in the early universe, we should see specific signatures in the stellar populations of these galaxies. James Webb's spectroscopic capabilities can test this, and studies are underway. If time dilation effects were at play, we might see unusual patterns in the distribution of galaxies across space and redshift. Large-scale survey programs are mapping this out. If the universe is older than we think, we should be able to reconcile the Hubble tension with new measurements. Multiple research groups are working on this using different methods. And if our cosmological model is fundamentally wrong, we should see other anomalies beyond just early galaxies. Interestingly, there are some other puzzles. The Hubble tension I mentioned, the sigma-8 tension, a discrepancy in measurements of cosmic structure. These might all be connected. The scientific community is in a fascinating position right now. We have extraordinary new data that challenges our theories, but we don't yet know which direction the solution lies. Some scientists are excited. Others are anxious. Everyone agrees we're in a period of potential paradigm shift. Let me take you deeper into what these galaxies actually look like and what their properties tell us. Because the more we examine them, the stranger they become. When astronomers analyze the light from these early galaxies using spectroscopy, they can determine not just their distance and age, but their composition, their star formation rate, even the types of stars they contain. And what they're finding is puzzling. Many of these early galaxies show strong emission lines from oxygen and other heavy elements. This is surprising because heavy elements require multiple generations of stars. The first stars, made only of hydrogen and helium, produce some heavy elements when they die. Then a second generation of stars forms from gas enriched by those elements, producing even more. This cycle takes time, yet we're seeing heavy element signatures in galaxies that appear to be only a few 100 million years old. The enrichment process seems to have happened incredibly quickly. There's more. Some of these galaxies show evidence of dust. Cosmic dust is made of heavy elements like carbon, silicon, and iron formed in stars. Dust requires not just one or two generations of stars, but many. In the modern universe, dusty galaxies are typically old and well-evolved. Finding dusty galaxies just 300 or 400 million years after the Big Bang is like finding a sophisticated city in a place where you expected to see only primitive settlements. Dr. Dirac Watson at the University of Copenhagen studies dust in early galaxies. In a 2023 paper analyzing James Webb data, he wrote, "The presence of dust in such early galaxies is problematic for standard models. Dust production and accumulation take time, typically 1 billion years or more. Yet here we are seeing dusty galaxies at cosmic dawn. And the morphologies, the shapes of these galaxies, are equally surprising. Some show disk-like structures with rotation, suggesting they've already settled into stable configurations. Others show signs of galaxy mergers, which implies there were even earlier galaxies that came together. One galaxy, designated as CRS 1019, observed at a redshift of 8.7, shows evidence of an active supermassive black hole at its center. This black hole is estimated to contain about 9 million solar masses. Now, supermassive black holes are common in large galaxies in the modern universe. The Milky Way has one with about 4 million solar masses. But we don't fully understand how these black holes grow. Current models suggest they start as stellar mass black holes, remnants of massive stars, and then grow over billions of years by accreting gas and merging with other black holes. A 9 million solar mass black hole existing just 650 million years after the Big Bang is hard to explain. Growth models struggle to produce such massive black holes so quickly. Unless, and this is what some researchers are proposing, supermassive black holes can form directly in the early universe without going through the stellar remnant stage. Perhaps under certain conditions, massive clouds of gas collapse directly into black holes with thousands or millions of solar masses right from the start. These are called direct collapse black holes, and while they're theoretically possible, we've never observed one forming. James Webb might be giving us indirect evidence that they exist. Dr. Priyangvada Natarajan at Yale University is a leading expert on black hole formation. She's proposed that direct collapse black holes could form in galaxies with specific conditions, low metallicity and intense radiation fields. The early universe might have provided these conditions more commonly than previously thought. If she's right, then supermassive black holes and galaxies could have co-evolved from very early times, each influencing the other's growth. This would explain both the early massive galaxies and the early massive black holes. But it also implies that the early universe was a far more dynamic and complex place than our models suggested. The cosmic dark ages might not have been so dark after all. Let me share something that really captures the magnitude of this problem. In 2023, a team led by Dr. Evo Lab published a paper identifying 6 candidate massive galaxies at redshifts between 7 and 9. These galaxies appeared to have stellar masses comparable to the Milky Way, which took over 13 billion years to assemble. The team calculated that these galaxies contained so much stellar mass that they would have needed to convert nearly all their available gas into stars with 100% efficiency. In the modern universe, star formation efficiency is typically only a few percent. Even the most extreme starburst galaxies rarely exceed 10 to 20% efficiency. 100% efficiency would require physics we don't understand. It would mean every atom of hydrogen in these galaxies turned into a star, with no gas lost to winds or outflows, no gas remaining unconverted. It's almost thermodynamically impossible. Lab himself said in an interview, "These galaxies are so massive that they're in tension with 99% of models from cosmological simulations. This means even our most advanced computer models of the universe can't reproduce what we're seeing." Think about that. Our supercomputer simulations, which accurately reproduce the structure of the modern universe, fail completely when trying to create these early galaxies. Either the simulations are missing crucial physics, or the observations are telling us something revolutionary about the early universe. Now, here's where the rabbit hole gets really deep. Because if we take these observations at face value, they suggest something extraordinary about the nature of cosmic evolution. Consider this possibility. What if galaxy formation isn't a slow, gradual process, but rather goes through rapid bursts? What if there are specific epochs in cosmic history when conditions allow for extremely fast structure formation? Some cosmologists are exploring the idea of triggered galaxy formation. In this model, the first massive stars or black holes release enormous amounts of energy when they die or accrete matter. This energy shocks the surrounding gas, compressing it and triggering rapid star formation in a chain reaction. One massive star dies, triggers the formation of 100 more. Those die trigger thousands, and so on. It's an exponential process that could, in theory, build a galaxy in tens of millions of years rather than billions. The math works, but it requires very specific initial conditions. And it predicts that these early galaxies should burn out quickly, exhausting their gas supply within a few 100 million years. Interestingly, some of James Webb's observations might support this. Some early massive galaxies appear to have already stopped forming stars by the time we observe them. They're quenched, as astronomers say, with little ongoing star formation despite having formed massive stellar populations. In the modern universe, galaxies typically quench when they run out of gas or when feedback from star formation or black hole activity blows away the remaining gas. But this process usually takes billions of years. Finding quenched galaxies less than 1 billion years after the Big Bang suggests that some process was rapidly building these galaxies and then shutting them down. It's star formation on fast forward. Dr. Catherine Whitaker at the University of Massachusetts Amherst studies quenched galaxies. In a 2024 paper analyzing James Webb data, she found several early massive galaxies that appeared to have stopped forming stars. She wrote, "The existence of massive quenched galaxies at such early times is a challenge to models. Not only did these galaxies form their stars incredibly quickly, but they also stopped forming stars incredibly quickly." Now let's connect this to something even more profound. The cosmic web. In the modern universe, galaxies aren't randomly distributed. They're organized into a vast cosmic web, a network of filaments and walls with enormous voids in between. This structure is shaped by dark matter, whose gravity pulls normal matter into dense regions. Simulations show that this cosmic web takes billions of years to develop. Early on, matter distribution should be much more uniform, with only small density variations. Structure grows slowly over time. But James Webb is showing us something unexpected. Even at high redshifts, even in the first billion years after the Big Bang, we're seeing hints of large-scale structure. Galaxies that appear to be clustered together, aligned along filaments. If confirmed, this would suggest that the cosmic web formed much earlier than expected, and that has implications for dark matter. Dark matter is supposed to drive structure formation. If structure formed faster than predicted, maybe dark matter has properties we don't understand. Maybe it clumps more efficiently, or maybe there's an additional component contributing to structure formation. Some physicists are proposing exotic forms of dark matter. Cold dark matter, the standard model, is made of particles that move slowly and clump gradually. But what if some of the dark matter is warm, or even hot, made of particles that move faster? This could change how quickly structure forms. Others are going further, suggesting that dark matter might interact with itself through forces we haven't detected. Self-interacting dark matter could collide and lose energy, allowing it to concentrate more rapidly in some regions. These ideas are speculative, but they're being seriously discussed in the context of the James Webb findings. And then there's the most mind-bending possibility of all. What if these galaxies aren't actually where we think they are in the timeline of cosmic history? What if our interpretation of redshift is wrong? Redshift is the foundation of cosmological distance measurement. We observe that light from distant galaxies is shifted toward longer, redder wavelengths, and we interpret this as evidence that those galaxies are moving away from us due to the expansion of space. The greater the redshift, the faster the recession, and the farther away the galaxy is. This relationship, codified in Hubble's law, has been tested extensively and is well established in the nearby universe. But here's the assumption we make. We assume that redshift at very high distances is caused only by the expansion of space. But what if there are other phenomena that can cause redshift? Some alternative theories propose intrinsic redshift, the idea that light can lose energy as it travels through space for reasons other than expansion. If light degrades over cosmic distances, objects could appear more redshifted, and thus farther away and older than they actually are. Mainstream cosmology largely rejects intrinsic redshift because it doesn't fit most observations. But a small number of researchers argue that in extreme conditions, like the early universe or near massive concentrations of dark matter, additional redshift mechanisms might operate. If they're right, if there's even a small additional redshift component, then the galaxies James Webb is seeing might not be as far away or as early as we think. They might be somewhat closer and younger, with more time for formation. But I want to be clear, this is a fringe idea. The evidence for cosmological redshift due to expansion is overwhelming. Proposing an alternative requires extraordinary evidence, and right now we don't have it. I mention it only to illustrate how deeply the James Webb observations are shaking cosmology. When the data doesn't fit, even well-established principles come under scrutiny. Let's step back for a moment and consider what all of this means in the bigger picture. Because this isn't just about galaxies or timelines. It's about our understanding of existence itself. For the past century, cosmology has been on a remarkable journey. We've gone from thinking the Milky Way was the entire universe to knowing we're one galaxy among hundreds of billions. We've traced cosmic history back to the Big Bang, mapped the cosmic microwave background, and developed a standard model of cosmology that explains most of what we observe. It's been a triumph of human intellect and scientific method. But science doesn't progress in a straight line. It advances through cycles of theory and observation, and sometimes observations reveal that our theories need to be revised or even replaced. This happened before. In the early 20th century, physicists thought they had a complete understanding of the universe through Newtonian mechanics and classical electromagnetism. Then came observations that didn't fit. The orbit of Mercury, the spectrum of blackbody radiation, the photoelectric effect. These anomalies led to the development of relativity and quantum mechanics, completely revolutionizing physics. Are we at a similar moment now? Are the James Webb galaxies the anomalies that will lead to a new cosmological revolution? It's too early to say, but the possibility is real. Dr. Wendy Friedman, one of the astronomers who led the measurements of the Hubble constant using the Hubble Space Telescope, said in a 2024 talk, "We're in an era where our observations are outpacing our theories. James Webb is showing us things we didn't predict, and that's exactly when science gets exciting. It's also when we have to be most careful, most rigorous, and most open-minded. And that's the key. Open-mindedness balanced with skepticism. We can't dismiss the observations just because they don't fit our models. But we also can't jump to radical conclusions without thorough analysis. What's happening now in the cosmology community is exactly what should happen. Intensive investigation, detailed modeling, exploration of alternative explanations, and a healthy debate about what the data means. Over the next few years, we're going to see a flood of new research. James Webb is still in the early stages of its mission. It's going to spend the next decade collecting data, and each new observation will either strengthen our current understanding or push us further toward a paradigm shift. There are specific observations that will be crucial. Deep spectroscopic surveys of hundreds of high redshift galaxies will reveal whether the early massive galaxy population is even larger than currently known. Studies of the stellar populations in these galaxies will determine if star formation efficiency really was higher. Searches for the first black holes will test theories of direct collapse. And there's another telescope on the horizon. The extremely large telescope, currently under construction in Chile, will have a 39-meter primary mirror. When it begins operations in the late 2020s, it will be able to study individual stars in some of these early galaxies, giving us unprecedented detail about their properties. We're also going to see advances in theoretical modeling. Astrophysicists are already running new simulations incorporating different assumptions about star formation, dark matter, and feedback processes. These simulations will make specific predictions that can be compared with observations. The truth, whatever it turns out to be, will emerge from this process. That's how science works. But let's think about the implications if our current cosmological model does need major revision. If the universe is older than we think, it changes our entire cosmic history. The timeline of events from the Big Bang to today would need to be recalibrated. This would affect our understanding of when the first stars formed, when galaxies assembled, and when the conditions for life emerged. It might also provide more time for life to evolve elsewhere in the universe. If galaxies formed earlier than we thought, then planets could have formed earlier. Life could have had a head start on billions of worlds. Think about that. While we estimate Earth formed about 4.5 billion years ago, if the universe is 15 or 16 billion years old instead of 13.8, there could be planets 10 or even 12 billion years old. Civilizations on those worlds could have billions of years head start on us. That's a humbling and awe-inspiring thought. If galaxy formation was fundamentally different in the early universe, it tells us that the cosmos evolved in stages with different physical regimes. The early universe might have been a period of rapid, violent assembly, followed by a slower, more gradual evolution in later eras. This could mean that the universe we see today, with its majestic spiral galaxies and orderly structure, is very different from the chaotic, energetic early universe. We'd be living in a calm, mature phase of cosmic history, but it also raises questions about the future. If the universe's evolution has gone through distinct phases, will there be more phase transitions ahead? What will the universe look like 100 billion years from now? A trillion? If our understanding of dark matter or dark energy is wrong, the implications are even more profound. These components dominate the universe's energy budget. Getting them wrong means we've fundamentally misunderstood the nature of reality. Modified gravity theories, for example, don't just change how we think about galaxies. They change how we think about space and time at the deepest level. If gravity behaves differently on different scales, then space-time itself might have properties we haven't discovered. This could open doors to new physics, perhaps to a quantum theory of gravity, perhaps to a deeper understanding of the relationship between matter, energy, and the fabric of the universe. And if the Big Bang wasn't the beginning, if the universe existed in some form before the event we call the Big Bang, then the concept of creation becomes more complex. Did the universe have a true beginning, or has it always existed in some form? Are we part of a cyclic cosmos that has gone through infinite iterations? What does that mean for the arrow of time, for causality, for the very concept of existence? These are questions that sit at the boundary between science and philosophy, and James Webb's impossible galaxies are pushing us to confront them. Now, I know all of this might seem abstract and distant from everyday life. You might be wondering, why does this matter? Why should anyone care about galaxies that formed billions of years ago? And that's a fair question. Let me tell you why I think this matters. Human beings have always looked up at the night sky and wondered, where did we come from? How did the universe begin? Are we alone? These aren't just scientific questions. They're existential questions, questions about meaning and our place in the cosmos. For thousands of years, these questions were the domain of religion and philosophy. Science, particularly over the last century, has provided answers grounded in observation and evidence. The Big Bang, cosmic evolution, the formation of stars and planets. These answers have been deeply satisfying because they're not just stories. They're supported by data, by measurements, by the scientific method. But they're also provisional. Science doesn't claim to have final answers. It claims to have the best current explanations based on available evidence. When new evidence emerges that challenges our explanations, science evolves. And that evolution is a feature, not a bug. It's what makes science powerful. The James Webb discoveries remind us that the universe is still full of mysteries, that our understanding, as advanced as it is incomplete, and that there's still so much to discover. In a world that often feels fully mapped and explored, where we have satellites photographing every inch of Earth's surface and can look up any fact on our phones, it's remarkable that we can still find fundamental mysteries. The universe is not yet fully known. It surprises us. It challenges us. And that's beautiful. There's also a practical side to this. The technologies developed for astronomy have countless applications. The sensors in your phone's camera were developed from technologies used in telescopes. Medical imaging techniques like MRI and CT scans evolved from astronomical image processing methods. GPS relies on our understanding of relativity. When we invest in understanding the cosmos, we're not just satisfying curiosity. We're developing technologies and knowledge that ripple through society in unexpected ways. And perhaps most importantly, studying the universe fosters a sense of perspective. In our daily lives, we're consumed with immediate concerns. Jobs, relationships, politics, all important things. But sometimes it's valuable to step back and see the bigger picture. We are inhabitants of a small planet orbiting an average star in one galaxy among hundreds of billions. We exist for a brief moment in cosmic time. And yet, we're part of a universe that's ancient, vast, and full of wonders. That perspective can be humbling. It can also be empowering. We're part of something grand. Our atoms were forged in stars. The calcium in our bones, the iron in our blood, the oxygen we breathe, all of it came from stars that died billions of years ago. We are, quite literally, stardust contemplating the stars. And now, with telescopes like James Webb, we're able to look back to the era when the first stars were born, when the first galaxies assembled. We're seeing our cosmic ancestry. The fact that those observations challenge our understanding doesn't diminish their value. If anything, it increases it, because it means we're on the edge of discovery, the edge of a potential breakthrough in understanding. As I wrap up, I want to leave you with some thoughts about where this mystery might lead. Right now, as you watch this video, scientists around the world are analyzing James Webb data. They're running simulations, testing hypotheses, writing papers. The pace of research is extraordinary. Within the next few years, we're likely to have a clearer picture. Maybe we'll find that galaxy formation can indeed occur much faster than we thought, with the right conditions. Maybe we'll discover that the universe's age needs a modest revision. Maybe we'll find evidence for exotic physics in the early universe. Or maybe we'll be forced to confront a more radical conclusion, that the Big Bang Theory in its current form is incomplete, that we need a new framework for understanding cosmic origins. If that happens, it will be one of the most exciting periods in the history of science. A paradigm shift on the scale of the Copernican revolution or the development of quantum mechanics. Future generations might look back on this era and say, that's when everything changed. That's when humanity realized the universe was even stranger and more wonderful than they imagined. And you watching this video right now, you're witnessing it unfold in real time. You're here at the beginning of what might be a new chapter in cosmology. So what does this all mean? Maybe the real question isn't how galaxies could be older than the universe, but what it means that we can even ask that question. For billions of years, the universe existed without anyone to observe it, to measure it, to ponder its mysteries. Then on at least one small planet, maybe on many, conscious beings emerged. Beings capable of looking back at their own origins, capable of building instruments to see across billions of light years and billions of years of time. We are the universe becoming aware of itself. And in that awareness, we encounter mysteries that challenge our understanding. The galaxies James Webb has found are impossible according to our current models. But they exist. The universe doesn't care about our models. It is what it is, and it's our job to update our understanding to match reality. These impossible galaxies are teaching us humility. They're reminding us that nature is more creative, more complex, more surprising than we give it credit for. And they're inviting us to think bigger, to question deeper, to imagine possibilities we haven't yet considered. Maybe the universe is older than we thought. Maybe time itself worked differently in the early cosmos. Maybe the Big Bang was just a transition in an eternal cycle. Maybe our understanding of space, time, matter, and energy needs fundamental revision. We don't know yet, but the journey to find out is going to be extraordinary. When I started researching this topic 18 months ago, I thought I was going to tell a straightforward story about new galaxies discovered by a new telescope. Instead, I found myself confronting questions about the nature of time, the limits of knowledge, and what it means when reality refuses to conform to our expectations. These galaxies, these impossible, beautiful, ancient galaxies, are more than astronomical objects. They're cosmic puzzles, philosophical provocations, invitations to wonder. And wonder ultimately is what drives us. It's what inspired ancient humans to watch the stars and tell stories about them. It's what inspired Galileo to point a telescope at the heavens. It's what inspired generations of scientists to build ever more powerful instruments, culminating in marvels like James Webb. We wonder because we're human. It's in our nature to ask why, to seek understanding, to push against the boundaries of the known. The universe we live in is roughly 93 billion light-years in diameter, at least the observable part. It contains hundreds of billions of galaxies, each with hundreds of billions of stars. It's been evolving for nearly 14 billion years, maybe longer. And we, tiny beings on a tiny world, have figured out how to measure it, how to trace its history, how to photograph its infancy. That's astonishing. That's a testament to human curiosity, ingenuity, and persistence. The fact that we've now found something that challenges our models isn't a failure. It's a success. It means we're asking the right questions, looking in the right places, and being honest about what we see. Science at its best is humble. It says, here's what we think we know, but we could be wrong. Show us the data. James Webb showed us the data. And the data said, think again. So we're thinking again. We're questioning. We're exploring. We're doing what humans do best, trying to understand. I don't know how this story ends. Maybe it ends with a simple correction to our models, a tweak that allows for faster galaxy formation. Maybe it ends with a revolution, a complete rethinking of cosmology. But here's what I do know. The journey is going to be fascinating. Every new piece of data from James Webb, every new theoretical paper, every new simulation is a step toward understanding. And you get to follow along. You get to be part of the generation that sees these mysteries unfold and hopefully resolved. So keep looking up. Keep asking questions. Keep wondering. Because the universe, it turns out, is still full of surprises. And some of those surprises are galaxies that shouldn't exist but do. Galaxies that are challenging everything we thought we knew. Galaxies that are older than the universe itself. And that, perhaps, is the most profound discovery of all. Not the answer, but the question. Not the solution, but the mystery. We set out to explore the cosmos, and we discovered that the cosmos is far stranger than we ever imagined. The impossible galaxies of James Webb are out there right now, their ancient light traveling across billions of light years to reach our telescopes. They existed when the universe was young, and they're waiting for us to understand them. What will we discover as we continue to study them? What will they reveal about the nature of reality, the history of the cosmos, the fundamental laws of physics? I can't wait to find out, and neither, I suspect, can you. Thank you for joining me on this journey into the deepest mystery in modern cosmology. If you found this fascinating, please share it with others who love pondering the big questions. Subscribe to Void Light Talks for more explorations into the cosmic unknown. Until next time, keep looking into the void. You never know what might look back.